Okay, well, good afternoon, everyone, and welcome to the w.r.t seminar for today. Today, we're very pleased to have Ladislav Rampášek from the University of Montreal and Mila. Ladislav is a postdoctoral fellow there in the group of Professor Guy Wolf. His current research interests are in the area of graph representation learning and geometric deep learning. He completed his PhD at the University of Toronto, where he developed latent variable models for cancer, treatment outcome prediction, as well as drug perturbation effect modeling. Today, Ladislav is going to talk about hierarchical graph neural networks and long-range interactions. Ladislav, welcome to the w.r.t seminar. We're looking forward to your talk.
Thank you very much for having me. Great pleasure to be here. And hello to everyone. So let's get started. So graph structured data are really abundant, and in recent years, it's been more and more hot area of research, developing models to process this kind of data, and such as social networks, knowledge graphs, biomedical networks, shapes and meshes, molecular data, and so on. And really all these data sets come in very different sizes and shapes, and the very different properties are important in these different data sets, even though they are all kind of graphs. And generally in this past year or two, the term geometric deep learning has been used as the umbrella term to cover this area of developing neural networks for Euclidean or non-Euclidean domains that involve these graphs, manifolds, meshes, gauges, and so on. And as I said, the type of properties that this data has and how to make the best use of the data and develop models with the right inductive biases has been really interesting. But in this talk specifically, I'll be talking about the long-range interactions in graphs and the approach with hierarchical graph neural networks for them. So first, I'll introduce the standard message passing graph neural networks very briefly. And then I'll show why we might need hierarchical graph neural networks for long-range interactions, and why the standard message passing GNNs have difficulties representing long-range interactions. And the majority of the talk I'll spend on our recent paper, the hierarchical graph neural net, and its empirical evaluation, specifically focused on these long-range interactions, which is the major contribution of our paper. Okay, so let's start with the introduction here. So graph neural networks, there are like many different types, but the most popular ones are based on iterative neighborhood aggregation via some a process also called the neural message passing, where a representation of a node is being iteratively updated by processing messages from its neighbors. So as we see on the right side of the slide here, the representation of A is updated by ingesting the representation of its neighbors in the original graph, processing them in some way, and then using that neighborhood aggregated information in some way to update the representation of the node. And this happens in parallel for all nodes in the graph. And we can stack this or layer this type of updates several times. And so, as I said, like this happens in parallel for all nodes. So also those are being updated. So in general, this framework or this paradigm is called the neural message passing, and follows this standard footprint, a blueprint of aggregating the messages from the neighborhood of a node in some kind of order invariant fashion, because in graphs we typically don't have ordering. If we do, then we need specialized methods. But in general, if you just assume nodes and edges, the standard composition of graphs, we don't have a sense of ordering. So we need invariant aggregation, and then an update function that takes in the old representation of the node and uses this aggregated information from the neighborhood to produce the new embedding. This can be parameterized in many different ways. So there's many different models, and one of the basic graph neural networks looks like this, where the invariant neighborhood aggregation is simply summing. You could also imagine using max or min or something of that sort, but summation is one of the most popular ones. So the representation of the nodes is just being added up of the neighbors, pushed through some linear layer, and then the representation of the node is being updated as a linear combination of the old one and of this neighborhood pushed through a nonlinearity function. And we can this way stack multiple of these layers, and that gives rise to graph neural networks. So as I said, we can parameterize this aggregation and update process with different neural networks or with slight variations, and that really gives a whole zoo of message passing GNNs that have been published in the past several years. Among the most popular ones is the graph convolution neural network, graph attention network, that is doing anisotropic filtering, where it has another separate model that computes an attention between the focal node and the individual nodes in the neighborhood to reweight them in some way, so that the aggregation can focus on some of the more important nodes in the neighborhood. Then graph isomorphism networks that use multi-layer perceptrons for the updates, and many more. So as you can see, by stacking a multiple of these GNN layers, the receptive field of the model grows linearly, because by each one iteration of the message passing, the number of or the neighborhood grows by one, right? And this, however, has several issues. If you want to get very deep graph neural networks, and which means applying this iterative process of message passing many times, it leads to oversmoothing, where the node representations tend to converge to local averages or even the entire average of the graph, and also to a problem called oversquashing or the bottleneck issue, where as we see that as the size of the neighborhood grows that is being aggregated, it's becoming more and more difficult to efficiently encode that information into the fixed size representation of the node. So, and at some point, the neighborhood is so big that this information simply can't be encoded, and then we are essentially losing that information. So even if we stack more layers, we really are not able to efficiently capture long-range information. So all of these come together, and cause this issue that that just conventional layer stacking can't really represent well the long-range interactions in graphs, because we would really need deep graph neural networks, but the really deep graph neural networks have these kind of issues. Very recently, there has been some approaches to mitigate this issue, but none of them really has been profound. They just result to some kind of injecting of the original information back in the graph, but really not adding a fundamental fix. So when do these long-range interactions matter? Typically, we would expect them to see in large molecular data sets when we're talking about large molecules like proteins, where there might be interactions or properties that span the entire molecule or a long distance that is not directly captured in the adjacency matrix of the graph. So is the case in physical simulations or for neural solvers in combinatorial optimization problems, where these problems are NP-hard. So we really need to represent the entire problem. And if this problem grows in size, then shallow graph neural net will not be able to represent the entire state. And since these problems are NP-hard, we expect that really the entire problem needs to be represented well and not just its local parts. Another example would be neural solutions operators for PDEs, where again you can have these kind of complex dependencies. And in many of these areas, it's not enough just to go global readout or some global pooling. Maybe for molecular data, as we'll see later, that might be good enough, but not always. So let's get into hierarchical graph neural networks and how they could provide some solutions to these problems. So by hierarchical graph neural networks, I understand that we are going to have multi-resolution representation of the original graph, such as the example here from diffpool, where we have the original graph that then has pulled some of these neighborhoods together into nodes on the next level and so on. And this way we have multi-resolution representation of the graph. And this kind of approach has natural potential to help with the long-range dependencies, because if we construct it carefully, it can decrease the diameter of the graph. And so the necessity for number of message passing rounds that we need to execute to really propagate the information across the entire graph. Next, it can help with oversmoothing, because the local information is preserved at the fine level of the hierarchy. We don't need to oversmooth the one representation that we have, and also with oversquashing in similar way. So while several hierarchical graph neural networks have been proposed in past 2 years or so, the literature have really not studied their ability to capture long-range interactions. They have focused on the standard graph benchmarks when it comes to graph learning tasks, and that this kind of direction is really the point of our study. So let's take a look at a few of the hierarchical approaches that have been invented in recent times. One of them is just this type of multi-resolutional readout, as for example the diffpool is, and several of these other works that I list here. They essentially create the multi-resolution representation, and then read out the information from each level and aggregate it together for the final prediction. But there is really not any communication or any computation going back and forth between the different resolutions. Another approach vaguely similar or related is encoder-decoder approach, such as that of GraphZoom, which is more just focused on dealing with really large graphs by compressing them to smaller graphs, doing the graph neural network on this smaller compressed graph where the connections are much shorter, and then unpulling the information back to the original graph. And then the more complex approaches use this U-shape computation approach, or sometimes also called V-shaped, akin to U-networks used in computer vision, where the information is being, the graph is first being pulled down to this multi-resolution representation, but then the information is also propagated back down the hierarchy and also laterally. The examples of that is graph units and multiple graph kernel networks. And then recently, another variation or extension of this approach are graph cross networks, where the information is passed a little bit in even more complicated fashion, in a way that the information also combines the view of one step finer and one step coarser representation of the graph. So these approaches are the most related to the one that I'm going to talk about. So let me just talk about them briefly. So GraphUnet uses GPOO pooling, which is based on selecting top k nodes from the original graph based on similarity score to a learned vector. So they are learning a vector p, and then based on cosine similar to this learned vector, those nodes that are most similar to it get pooled and create the next coarser representation of the graph. And at each level, one iteration of graph convolution neural network message passing is done. And this way, we go down the hierarchy, and then going back up means unpooling, going back to the one step finer representation, applying GCN again, and unpooling again and applying GCN again to get the final representation of the nodes. That this way combined the representation from the fine and coarse view of the graph. In the graph crossnets, the pooling is done by vertex infomax pooling, that is based on selecting nodes that have high mutual information with so basically packing nodes that are very similar or can predict each other. They have very high mutual information together into a node on the coarser representation. So this way the graph is downpooled, and the multi-scale representation is created, and then the messages are being passed not just within each representation, within each resolution view, but also between the neighboring ones. And this process is iterated a few times, and then eventually read out from all these resolutional views. All right, now I'm getting to our work, Hierarchical Graph Net, HGNet, which is principally similar to that of the GraphUnet. And what we really focused on is the effect of different pooling to create the hierarchy, and how this actually, and whether this type of construction of graph neural networks really can represent long-range interactions, because it's something that really has not been studied by the prior literature in great detail. And similarly, so the method is basically composed of two major steps, and that is that one of building the multi-resolution representation, and then that of the message passing. And we provide two ways, or explore two ways to create the hierarchy. One is based on edge pooling, and the other is based on Leuven method for community detection. So that's a fixed, unlearned, non-differentiable, right, way of creating the hierarchy. while the edge pool is differentiable and learned with the remainder of the model. So the edge pool scores each edge. It's a method by Deal from 2019, where we take the representation of the nodes at the end of each edge, pass it through a linear model to get the score for this edge, and then after we have all these scores, we greedily pull as many edges as possible, and this way it's not the optimal matching, of course, but works pretty well in practice. And this way we can create coarser and coarser graphs, and that gives rise to this kind of hierarchical representation where we're down pulling the graph by contracting these edges. The w.r.t method is based on greedy maximization of modularity of each community in the graph. So it's pretty much clustering based on optimizing this modularity score that measures density of links inside the communities compared to the links between communities. It runs roughly in log n time, and it's deterministic up to a random seed. Again, so here's the visualization. It yields a way of, in some way, a clustering, and we pull those clusters into nodes on the next layer, and we use typically average pooling. So we just compute average of the node features, and then compute the induced graph, and that is the next coarser view of the graph. And here are some examples. If we look at an example from the enzymes dataset, so this is a protein. Here the vertices that are of the same color got evaluated as being part of a single community. So those are then contracted at the next layer. For example, here, and these get pulled to this one, and so on. And again, we iterate this process to get the entire hierarchy. So this is how it looks like for some of these proteins from these data sets. Also, this D&D data set is a bit larger proteins, and here you can see what kind of hierarchical representation we are roughly getting using the w.r.t method. NCI, these are small organic molecules, and IMDb binaries so are these ego networks of actors derived from IMDb. All right. So after we have the hierarchical graph, either by edge pooling or by w.r.t method, either way, we have this kind of recipe for creating this multi-resolutional representation of the graph. We're going to apply the hierarchical message passing, and that can be and that is applicable to both graphs. So it doesn't matter whether we got the graph by using edge pooling or w.r.t. So we have just one way of doing this message passing, and that is composed of computational paths up and then down the hierarchy, which is the same principle as was in the graph unit that I talked about a little earlier. So how it looks like, we start with the original graph, we apply a graph convolutional layer, then we apply edge pooling with mean aggregation to pool the original graph G0 into graph G1, and where we apply the GCN message passing layer again, and iterate this process as many times as we can, or up to some predefined number. So, but we typically use hierarchies of depth only 2 or 3 hierarchical levels deep. and this way we go up the hierarchy, and then we go downwards in the downward computational path, where we use relational and graph convolutional neural network, where we treat the edges coming from the cluster representation. So here that's the dotted line from the kind of parent node as a special type of an edge. So the model can learn that it's processing this hierarchical information in a different way than any other messages coming from the neighbors. And this way we go back down to the original graph and arrive to the final representation of the nodes in the graph that we started with. All right, so let's look at the computational complexity of this kind of construction when using edge pool. Let's assume that one round of this edge pooling will contract the graph of n vertices to a graph of at most n over m vertices. So it's contracting by a factor of m, and it's exactly m if it's perfect matching, and it's going to be a little bit more if it's not, but even for a random graph n1 over n, it's bounded by a constant, so we can assume that there exists a constant m for which this holds with for these at least random graphs. So under this assumption that we have this kind of constant, then we can easily compute that the number of nodes in the entire hierarchical graph is going to remain asymptotically unchanged. So it's still going to stay O of n, of the original number of the nodes. And for the number of edges, we can do a similar calculation as well. So that means that for the construction with edge pool, we can assume under reasonable assumptions that the size of the graph remains asymptotically the same. So we are not blowing up the graph by in some large way, and also this implies that we are expecting to have at most log n layers or of these hierarchical levels, and this means that if the original graph was connected, so there are no disconnected components, then the length of the shortest path between any two nodes is upper bounded not by the diameter of the graph, but also by the logarithm of the number of nodes. And this might be considerably less for sparse graphs, such as we saw the proteins that have this kind of chain-like structures. So and then also other consequence of this construction is that the receptive field of this model grows exponentially with the number of hierarchical levels and not linearly with the number of stacked layers, as we saw standard GNNs do. So we don't need to stack the diameter, the number of GCN layers equivalent to the diameter of the graph to really propagate the information through the entire graph. All right, so let's get to the experimental results. So first we looked at the standard benchmarking data sets that I call legacy because they've been around for quite a long time. They are very small, and while they've been still quite often used for benchmarking graph neural networks, in the past year there's been definitely a push to move away from them towards more complex data sets, and as you'll see, as I'll show, that's for a very good reason, because these data sets typically don't have long-range interactions, so it's really difficult to then show that these models really do what they are expected to do or claim to do. And we'll try to make these models, these data sets a little bit harder, but still there's only kind of there's definitely some limitations imposed by these data sets. And so we benchmarked our model also on Open Graph benchmark that has much larger data sets. And we also constructed a new color connectivity task that we designed specifically to isolate the task of learning long-range interactions. Okay, so one of the standard benchmarks are these citation networks such as CiteSeer, Quora, and PubMed, and for that we used baselines, the graph attention model, graph convolutional network, HGNet, the graph isomorphism networks as well. And as you can see, the standard models with just 2 layers are kind of hard to beat. And this is not surprising because these citation networks are notorious for having really high homophily. So the nodes of the same class tend to be in the same neighborhoods, and so the long-range information is really not needed, and you can do very well by just local smoothing, or in some cases even by ignoring the entire graph structure. So these data sets are really limiting in this sense, and don't serve the purpose of benchmarking these kind of complex models. We tried to make them to still reuse this data in some way. So our idea here was to enforce that nodes selected for training, testing, or validation are at least k hops away. In these citation networks, you have just one large graph, and the nodes are randomly selected for training, validation, and testing, but they can be neighbors of each other, right? So we resampled the data set in a way that they are at least k hops apart. So this way, the model can't really leverage this information easily unless it has a receptive field that goes beyond this k that we sanitized. And you can see it here that if we resample the data set for k equals 1, so something like what is illustrated here, the models with just 1 layer definitely drop in performance and recover the performance only after they have 2 layers, so they can actually reach that far, while the hierarchical networks with just 1 hierarchical level have larger receptive field, and right away they provide the same performance as the baselines with more layers. And we tried this also for k equals 2, and the results are similar, but we are quickly running into the issue of the high homophily in the data sets, that really if we were to go for k equal 3 or so, the information from the neighborhood is really not that important. So this way we at least verify that these hierarchical models such as GraphUNet and ours do increase the receptive field, but these data sets are really not as challenging to show a large benefit. Another set of standard benchmarking is for the task of graph classification on data sets such as Colab, IMDb binary, IMDb multi-label, DND, where it's distinguishing enzymes and non-enzymes, NCI, where we're classifying molecules for whether they are active against the lung cancer or not. Then enzymes and proteins are also based on proteins, and they are predicting different kind of types of properties of these proteins, whether they are enzymatic or not, and or to what kind of family they belong to. And as we can see, the hierarchical models are pulling ahead in some, but not in the others. And the results are kind of all over the place in this sense. And really the question is then whether which of these data sets really contain actually any long-range interactions, and whether the data sets are really challenging enough to for these models. And for that, we decided to do this graph fragmentation study to probe the importance of long-range interactions in graphs. And we're doing it by fragmenting the graphs, disconnecting components, and observing the change in the predictive performance of a graph convolutional network baseline model. So take this example of a protein from the enzyme data set. And what we're doing, we randomly select a node, extract its, in this case, 3-hop neighborhood, remove it from the graph, and then iterate again. Take the leftover graph, select a node, extract its 3-hop neighborhood, and so on until the entire graph is consumed. And then if there were any like long-range interactions or something, then we effectively we are removing them and limiting only to the local information. So if you do that to the IMDb binary data set of the actor-eager networks, we can see here the original graphs, and here their fragmentation for k = 1 or k = 2. And as you can see, a lot of these graphs are actually very densely connected. So this is literally a click. And for some, they are still just 1 hop away. And only for a few graphs, we're actually seeing some kind of change caused by this fragmentation. And this immediately pretty much tells us, right, that this data set doesn't really have any long-range interactions, because the diameter of the graphs are so small. It's a little bit different for D&D data set of proteins. There's that have a lot larger diameter. The same goes, or similarly goes for other protein data sets, such as enzymes and proteins, which actually have the same, that they have the same domain of graphs, just different prediction tasks. And then after we fragment this, let's look at what we get here. We look at the relative performance of these different modifications of the data set and of a graph convolutional network with 1 to 5 layers. And we look at the relative performance to the best performing model. So let's say for this NCI here, we computed the performance for GCN with 1 layer, 2 layers, 3 layers, 4 layers, 5 layers, and the 5-layer one was performing the best, right? And with 1 layer you get to 82% of the performance of the model with 5 layers. And if you fragment the data sets in the graphs in the data set to k = 1, 2, or 3, you are observing this kind of drop in the performance. And this shows that in case of, let's say, NCI, there are probably properties or that go beyond just this local information of k hops of 1, 2, or 3, because as we're removing that information, the performance keeps dropping, and is the best for k = 3, where the most is preserved, and then the best one is the original one. But this is not the case for many other data sets. Let's say the D&D data set, which also has large graphs of proteins, but actually the best performing model is just a single layer graph convnet. And with more layers, we are not really improving the performance. It actually drops. And also, if we fragment the graph, we are not seeing any major drop in the performance. So even though the domain on which of this data set might have interesting structure and is fairly complicated, the prediction task probably is not. In this case, it's predicting proteins that are enzymes from those that are not enzymes, and probably there's something very simple by which the model can tell it, and hence this data set is not really that suited for testing whether our model can better represent long-range interactions or not. So the result, at least from the analysis of these 5 data sets, we can see that the largest drop in performance by making this fragmentation analysis we see with the NCI and the enzymes data set, and the least is in this DND and the proteins data set. And it's really interesting to see, because a lot of these data sets are very similar in sense of their domain. It's just that the prediction task is different. So even though the data set might be relatively complicated, the prediction task might not, right? And then hence that benchmark might not be that interesting for actually benchmarking novel models. And so that's why these data sets are really not sufficient for testing the ability to capture these long-range interactions. And as we saw, the NCI and enzymes were actually the ones that we've seen to exhibit most of this property, and that's where interestingly our models performed really well. Then we also tried larger molecular data sets from the Open Graph Benchmark data set, particularly the MOL-PCBA and MOL-HIV. These are much larger data sets. The previous ones have only like around 500 to 1,000 graphs. These ones, I think MOL-PCBA has close to 500,000 molecules in the data set. So we're finally like getting to a little bit larger data sets. And while our hierarchical models don't beat state of the art by any means, but they are definitely outperforming the conventional layer stacking. So our HGCN with just 2 hierarchical levels, where we use GCN at each level, actually beats stacking of 5 layers of GCN. So that's here. And irrespective of whether we use the edge pooling or Louvain to actually compose the hierarchical graph. For MOL-HIV, it's the same case, but MOL-HIV seems to also not be such a difficult benchmark in the sense that the performance of all these models is relatively similar. Of course, what we are seeing here is that for the MOL-PCBA particularly, what is very powerful is this virtual node extension of the graph convnets, where what it means is that there's an additional kind of readout at each layer that pulls the information from all the nodes, irrespective of the connectivity in the graph. So it's providing this kind of additional capacity or a capability for the model to just get the kind of aggregated information from the entire molecule. And in case of MOL-PCBA, that's very important. We see that really improves the performance a lot. And that might show that in this case, for this benchmark, the global property, like the global of the molecule, is more important than maybe some kind of complex dependencies. It's some kind of global readout can just do really well. So in summary, then we're seeing that a lot of these benchmarks are either too small or too simple, or maybe complex, that we can't really isolate the property of testing ability of the models of capturing the long-range interactions. So we decided also to design a synthetic data set that would focus specifically on that and not be perhaps plagued by other difficulties or complexities of the data. So we decided to create this color connectivity color connectivity task, where we take a graph and randomly color half of its nodes red and half of its nodes blue, in a way that the red nodes create one connected island or two disjoint islands in this graph. So you can see it here on the left side. Here the red nodes are connected, and here on the right side they form two islands. And the task then for the GraphNet is to predict whether it's one or the other case. And we've done this on 4 different graphs, so 2 different sized grids, 16 × 16 or 32 × 32. Or then we took 2 road networks, the Euro road network with something over 1,000 nodes, and Minnesota road network with something over 2,500 nodes, and created around 15,000 graphs like this as the data set, and trained the models on them. And as you can see, as the graphs get more complicated, and especially with large diameter, Euro road has a diameter of around 60. The baselines are starting to faint away and don't go much above 50%. As opposed on a smaller graph, they can still get to decent performance. For some reason, we've seen graph isomorphism networks perform fairly well, but the graph UNet with the similarity pooling really fails in this case, because the similarity-based pooling is not really a right match for this type of data. So it can't really create an informative hierarchy, and really loses the structure. So even though it can do hierarchical propagation, it really can't capture the connectivity of the red nodes in the data. And here we see the benefit though of the hierarchical graph nets with both HPool or Louvain. But I think I'm showing just Louvain here. Sorry, the HPool version here. In these models, the receptive field grows exponentially with the number of hierarchical levels, and so the performance goes up much faster than compared to the baselines. And with that, I'll conclude. So we've seen that the standard message passing GNNs have difficulty representing the long-range interactions in graphs, especially because of the bottleneck issue and oversmoothing issue. And hierarchical graph nets can help with this by shortening the path lengths over which the messages have to be passed if this hierarchy is well constructed. It then also increases the rate with which the receptive field grows as the network gets deeper. And we can also insert some kind of inductive bias about the data into the model by choosing the right type of pooling, or designing a one that is most flexible, but it's definitely another kind of hyperparameter in a way. And one of the really important parts here is that the benchmarking is really non-trivial, and that many hierarchical models have not really considered benchmarking this type of properties, and that actually many of the data sets out there are not suitable for it. So you really can't see or test the power of the models to really capture these long-range interactions. And that's what we've studied, and came up with some with that color connectivity task. But I can imagine that we could do more in this sense as well. And with that, I would like to thank you for the attention, and thank my postdoc supervisors, Guy Wolf and Will Hamilton, as well as my student collaborators. And this work was done at Mila, UDM, and my postdoc is funded through Ivado. So thank you very much for attention.
All right, thank you, Ladislav, for a very interesting talk. So just a reminder to the attendees, if you'd like to ask a question, at this stage you have two options. One is to either type your question into the Q&A and I can relay it to Ladislav, or you can raise your hand and I can unmute you. Ladislav, maybe I'll start off with a question or two of my own. Actually, I was wondering if you could revisit the intuition behind the reverse GCN process in the sort of, I think you called it the RGCN part of your algorithm, and sort of what that's adding into the representation that's not there when you just do, like, for example, straight edge pooling alone. Like if I only did the left-hand side as opposed to the left and the right-hand side.
So at the end of the day here, we would, to get the node representation, we would need to somehow combine the information from this cursor views. And either we could do it by some kind of pooling where we like take the, for each node in the original graph, we would also take all its parents in the hierarchy and combine it by some RNN or do some kind of pooling, or so that would be something akin to the approach that I would call this multi-resolution readout.
Right. Right.
Yeah, or the more complex one is to actually run a GCN to do that.
Okay, so if you just do the left-hand side, you need to read out at each layer of the hierarchy.
Yes, or for graph level tasks, such as you could maybe pull this down to just a single vector. And that's what a lot of the pooling algorithms were actually designed for like a diff pool and so on. Right. They were specifically made for the graph level representations. But even for graph level representations, we have seen benefits from actually doing this unpooling and propagating the information back down, because probably a lot of the low frequency information gets lost this way. So it's still better to do the propagation back down.
Oh, interesting. Oh, thank you. Then for the two pooling methods that you considered in your work, I think I missed this. Are those unsupervised methods like edge pool and the other one, or are they also are there learned parameters in those that are trained?
This edge pooling one is learned. So the parameters that are being learned there are in the scoring model that takes the representation of the nodes at the end of an edge, and that it then scores that particular edge. And how this is actually trained is that this score is then added in a smart way to the representation of the new node that is created by pooling this edge into one, by like contracting this edge into a node on the next level. So here, for example, when this is being pulled into a node that represents the nodes 2 and 3, this score is actually added to it in a way, so that when you're back propagating the graph learning loss, you're also learning the scoring function for this edge contraction. Yeah, and the Louvain one is not trained. It's just essentially a community detection algorithm that doesn't have learnable parameters.
Right. And in your numerical results then, or do you have any conclusion in terms of whether there's a significant advantage between edge pool and the Louvain method?
I've seen
in the context of your network. Yeah.
Yes. we've seen better results with the edge pool, but it does change between the data sets. But as I said, like with most of the data sets are fairly small, so I'm not sure if it's really significant. But for the larger graphs like the OGB, the edge pooling did perform better. So that's here. The edge pooling worked better for the mol PCBA, the more challenging task, but actually didn't perform better for the mol HIV.
But then it reverses on the other one. Right?
Yeah.
Okay.
So it's kind of a wash. I think it's yeah. I have not seen any clear benefit to one or the other. I guess I can say that.
Okay. I'll ask one more question. One of the two issues that you mentioned with very deep graph neural networks is is over squashing or bottleneck sort of issues in terms of trying to collapse a lot of information. Can you describe a bit more how your method alleviates this problem, if it does?
Yeah, so one reason why the oversquashing and oversmoothing even happens is that to propagate the information through the graph requires as many message passing rounds as is the diameter of the graph.
Right.
To do at least one kind of information propagation round through the entire graph, right? And if we construct if it's a relatively sparse graph and we construct the hierarchy well, then the length of these shortest paths gets shorter. Like we can connect these nodes through the hierarchy with just log n hops. Okay. And so we actually need less message passing rounds to propagate the information. Okay. And also, since we are not using just the representation of capacity of the original graph or the fixed vector size, but also have the representation of the graph in multiple resolutional views, we are not collapsing all the information into a single vector. Maybe like so at least these different frequencies as if are separate from each other and not pulled into one vector. So those are the kind of intuitions why the hierarchical model has some kind of inherent potential to alleviate the issue.
Right. Okay, that makes sense. Great. Thank you. Well, for those of you left in attendance, are there any questions you want to add? One. Okay. Looks like I don't see any. So anyway, well, Ladislav, thank you once again for the talk. I really enjoyed it. And for those of you in attendance, of course, we hope to see you again in future weeks. Thank you, everyone.
Thank you very much for having me.
Yeah, thank you. Yeah, that's great.